In this module, we will try to get an understanding of a refrigeration system, look at its key function, and then also we will examine the characteristics of different refrigerants. The main function of a refrigeration system is to transfer heat from a cooling chamber to another location where that heat can be easily discarded. Now, this function is common to every type of refrigeration system, whether you are looking at a home refrigerator or a large refrigerated warehouse. Now, this transfer of heat is accomplished by using a refrigerant. Now, refrigerant is a chemical substance. We can actually consider refrigerant to be similar to water. As you know, water can change its state from liquid to gas. So the same thing with the refrigerant. However, unlike water, a refrigerant has a much lower boiling point. As you know, water boils at 100 degrees C, but in case of a refrigerant, for example ammonia, it boils at minus 33.3 degrees C at atmospheric pressure. So similar to water, ammonia also needs heat of vaporization to change its state from liquid to vapor. And it discharges heat when those vapors are condensed back to liquid. We can change the boiling point of ammonia by changing its pressure. For example, we can have ammonia boil at 0 degrees C at 428.5 kilopascals. So this way, by adjusting the pressure, we can have refrigerants boiling at different temperatures and thus accomplish desired temperatures in our cooling chamber. Let's look at how we select a refrigerant, and we can do that by looking at the characteristics of a refrigerant. Now first, we want the refrigerant to have high latent heat of vaporization, so that a small amount of refrigerant, when it vaporizes, it should be able to absorb large amount of heat. So in this way, we will need small quantities of refrigerant to accomplish the cooling process. We want to avoid excessively high condensing pressure for a refrigerant. If the condensing pressures are too high, that means that you will need to run the refrigeration system at high pressures. That means the wear and tear on the equipment will be much more, and therefore the costs will be higher. We want the freezing temperature of the refrigerant to be below the evaporating temperature. Now, as we will see later on, in a refrigeration cycle, the state of the refrigerant varies from liquid to vapor, and then it is turned back into liquid. And it flows within the refrigeration system. Now, if that refrigerant turns into a solid, then we will have a problem, because then the refrigerant will not be able to flow inside the pipeline. So we do not want the refrigerant to freeze at temperatures that we are trying to accomplish in our cooling chamber. It should have a sufficiently high critical temperature. Now, a critical temperature is a temperature where chemical substance get into an unstable state. We certainly do not want that, so the refrigerant should have a fairly high critical temperature, a temperature that we will never reach in the refrigeration system. The refrigerant must be non-toxic, because we are looking at food applications. It should be non-corrosive to the equipment, the pipeline and so on, and it should be chemically stable. Now, we will talk about the stability part in a short time, but we do not want the refrigerant to be unstable chemical. It should be easy to detect leaks, since the pressure of the refrigerant will be raised at some point in the refrigeration system. If it begins to leak from the system, we should be able to easily detect it. And finally, the cost of the refrigerant should be low, since refrigerant will be required throughout the life of the refrigeration system. Now, some of the common refrigerants are ammonia. There is a designation that is provided for different refrigerants by ASHRAE, the American Society of Heating, Refrigeration and Air Conditioning Engineers. The nomenclature they use is begins with R and then a number. So ammonia is R717. And as you know, the chemical formula for ammonia is NH3. Another refrigerant is Freon 12, and the designation is R12. The chemical formula is CCl2F2. It's a dichloro-difluoromethane. Freon 12 was used around the globe for a number of years. However, its use has now been banned because of the problems that Freon causes with the atmosphere. The replacement for Freon 12 is HFC 134A, also designated as R134A. Chemical formula CH2FCF3. It's 1112 tetrafluoroethane. Now, chlorofluorocarbons, also called CFCs, are extremely stable. And when a refrigerant is extremely stable, then it may have a long life in the atmosphere and may even migrate into upper atmospheres over time, where the chlorine molecule will react with ozone and thus depleting ozone concentration. And of course, ozone is important in the upper atmosphere because it blocks the ultraviolet rays reaching the Earth's surface. So according to the Montreal Protocol in 1987, a time was set for all nations to phase out the use of CFCs so that we do not cause damage to the ozone layer. So the replacement for Freon 12 was the HFC 134A refrigerant that we will look in more detail in some of the following modules.